How's it everyone who's watching this? This is my 36th video on channel, and today we're going to be going over Chapter 4 of Intensive Science and Visual Philosophy by Manuel DeLanda, titled Virtuality and the Laws of Physics. In the last episode, we finished our examination of the role of time in Deleuze's philosophy, introducing the virtual equivalent of Chronos, Ion. In this episode, we'll move away from the specifics of actualization, and instead focus more on the epistemological side of Deleuze's thought. This and the next video will draw quite heavily on what we've gone throughout the series, so I recommend watching the earlier videos first. Getting right into it, DeLanda begins the chapter with a recap on the idea of a flat ontology that we first examined in episodes 4 of the series. Essentially, rather than there being some kind of hierarchy of ontological significance, where, for example, organisms are inferior to the species that they make up, which in turn are inferior to genera, a flat ontology instead posits every entity is an individual in its own right. Moreover, these individuals are themselves always made up of and part of other individuals. For example, cells make up organisms which make up species which make up genera. Although this might give rise to an idea of a hierarchy, none of these are closer to being than any other. To borrow DeLanda's words,
there is no room for reaffine totalities. In particular, there is no room for entities like society or culture in general.
A nation-state, for instance, is no more ontologically significant than a single person. Rather, it forms a social individual, simply having a greater spatio-temporal scale than its constituents. In the same way, DeLanda says that the use of the word science without qualifications is problematic. It acts as if there's some sort of abstract totality, when in fact there's nothing of a sort. In his eyes, what we have to instead do is strive to work out the processes that give rise to specific individuals, like topology or hydrodynamics. To begin with, we can look at the cells that make up each field. As he says,
in the case of classical mechanics, these components are, roughly, populations of mathematical models, populations of phenomena, populations of experimental skills.
The main takeaway from this part of the chapter is that science is characterized by a fundamental disunity, each individual field being composed of a myriad of diverse populations. The first focus of this chapter is this fact. DeLanda is seeking to explore how to think about individual scientific fields and the obstacles faced by philosophy in that endeavor, namely the omnipresence of essentialist and typological thought. Here, he turns to the role of so-called exceptionist laws, like Newton's laws of motion. Often treated as general truths from which everything follows mechanically, the dynamic and productive aspect of these laws is too commonly ignored. Central to this problem is the way in which causality is often put aside, philosophy treating laws as if they exist in a vacuum. In DeLanda's words,
contrary to a popular misconception, philosophical approaches to scientific practice have thrived. In a world devoid of causes and ruled by laws, stating constant regularities.
The first task of a Deleuzian epistemology, he says, must be to take causal connections, which he terms genetic, out of the strange limbo they've been resigned to. The second task involves rescuing dynamic models from being reduced down to static linguistic representation. In DeLanda's eyes, these two tasks are necessary for removing essentialism from classical physics. He begins by outlining the epistemological theory of deductive nomology, where, as he says himself,
scientific explanations are treated as logical arguments consisting of several propositions, one of which must be an exceptionalist law.
Essentially, the truth of a certain thing can be determined deductively by working out the truth of its premises, using an exceptionalist law as a guideline. In such a framework, there is no room for dynamics or cause and effect. Things just are true or false. This poses a problem because it leads to a few true statements, the laws, being treated as axiomatics. The truth of the theorems that result from the application is contained in them themselves, giving them the same status as essences in a sense. In DeLanda's eyes, it's the focus on these linguistic games of true and false that has to go. He endorses instead a new strand in the philosophy of science, where theories are characterized first and foremost by their causal or genetic components. For these philosophers, he states,
explanations, rather than being simply logical arguments, involve a complex use of mathematical models of different types.
Like we went over earlier, theories in this framework are formed from populations of models, each with their own historical baggage and genetic relationships. there is no pretense that they are the be-all and end-all of science. No. Rather, this way of thinking about theories stresses the openness of science, never being fully exhausted. For a time, one population of models may seem to be closed, but inevitably, changes will occur. At this point, he introduces the philosopher Nancy Cartwright, who argued that the fundamental laws of physics are false, or, to be more specific, that they lie. The heart of her argument rests in the fact that laws, like Newton's law of gravity, can only be accurate in the most artificial of circumstances. It's general, sure, but that doesn't really matter at the end of the day. It is only very rarely that Newton's laws can be applied properly, since there's always interference from other things, like electromagnetic fields. This way of thinking about laws shows us their fundamental problems. The only way to make them strictly true would involve sacrificing their generality, thus emptying them of all the things that make them so appealing in the first place. As our author summarizes, her position is that
the objective content in physics does not lie in a few fundamental laws, but in a large number of causal models tailored to specific situations.
DeLanda sees this as a step in the right direction, but he doesn't fully agree with Cartwright. This is because of her claim that laws serve to unify and organize the population of models that they are connected to. In DeLanda's eyes, the problem here is taking that unifying principle for granted. It must first be accounted for. To this end, he introduces the notion of a calculus of variations, developed by the mathematicians Leonard Euler and Joseph Louis Lagrange, as a way of posing what DeLanda terms mechanical problems. How it works is through a shift from looking at problems in terms of the causal effects of different forces to a focus rather on finding, the aim being to discover the possible processes that can change a system from one state to another. In the end, they are able to find sets of singular points, the minima or maxima, or rather the minimum and maximum states of certain processes. In this way, they develop their own theory of singularities, not unlike that of Deleuze. The point in relating this to us is to show how laws, more specifically variational ones, sidestep causality and thus can act as unifying forces. They are mechanism independent. Just like in Deleuze, Euler's system can be thought of as virtual, the mathematician himself additionally saying that it exists parallel, not opposed to, the actual or causal. Moving on, it's always a question of problems. In Deleuze's eyes, what's important about someone like Newton is not the development of some general principle, but rather the posing of an objective problem, defined by the simplest distribution of singularities. In hopefully some more clear words, Newton didn't deduce some general essential truth, but rather posed a problem, defined by being basic and thus by its ability to apply to many, but not necessarily all, situations. It's a problem in the sense that it generates some sort of understanding, or sense, that requires explanation. However, in DeLanda's words,
this conclusion assumes that the traditional axiomatic approach to physics can be replaced by a problematic approach, but this replacement needs more justification.
To supply this justification, he invokes explanatory problems and the relationship to physical phenomena as a case study. This problem asks the question why. Why does this phenomenon take place, but not this one? Such questions almost always involve causal elements, the mechanism behind the phenomenon. However, something a bit less obvious is the role of a quasi-cause, covered in earlier episodes of a series. It enters into the frame as a way to explain why there is regularity between different phenomena, even independent from the mechanisms that give rise to them. Taking a step back, he offers the phrase, why did event X, as opposed to Y or Z, occur, as the template of an explanatory problem. Using a concept derived from the mathematician and philosopher Alan Garfinkel, he describes the bracketed, as opposed to, section as a contrast space. Confusion arises when multiple people approach the same problem with different contrast spaces. For example, in the case of a priest asking a criminal why he robbed a bank, the response is that, well, that's where the money is. They aren't talking about the same thing, because their contrast spaces don't align, leading to the priest failing to connect to the criminal. Following Garfinkel, DeLanda says that there's something to contrast spaces that can't be captured in language, even in the case of seemingly linguistic situations like the one we just went over. As opposed to the possible worlds of modal logic, which we examined in episode 2 of the series, they are more like state spaces, the geometric representations of all the possibilities of a given system. These possibilities aren't arranged willy-nilly, as it were. Rather, they're structured by a distribution of attractors. In other words, singularities that guide the long-term tendencies of a certain process. This is as true for contrast spaces as it is for state ones. Applying the notion to problems, Deleuze says this.
There are problems which are false through indetermination, others through overdetermination.
What he means by this is that there are some problems that have too dense a distribution, and others too sparse. To give context for an example of these, just take the case of a cycle of increasing and decreasing prey and predator populations. The number of prey increasing leads to a similar increase in the predator population as more food becomes available. However, at some point, a critical threshold is met, and the number of predators becomes unstable, leading to a decrease in prey populations. This in turn leads to a decrease in predators when food becomes scarce. If we posed the problem of why this occurs on the level of individual prey and predators, we would get something overdetermined. There are too many singularities or attractors involved. In other words, too many alternatives to answer the question in any useful sense. However, if we expand to look at the problem on the level of populations themselves, everything becomes clearer. It becomes well posed. DeLanda puts this in linguistic terms by saying,
one problem is, why was this rabbit eaten as opposed to not eaten? While the other is, why was this rabbit eaten by this particular fox as opposed to this or that other fox?
The second problem is overdetermined in the sense that it contains a lot of irrelevant information in its contrast space. If there's a great enough density of foxes, all rabbits will eventually be eaten. The identity of one or the other fox doesn't really matter. This sort of problem is what Garfinkel, and by extension DeLanda, calls explanatory unstable. What this means is that its explanation has too fine a net. There are simply too many possible answers, the causal relationships between them thus being unstable. The notion of explanatory stability is crucial to a flat ontology, like the one we've been developing in this series, since it allows us to create something of an objective criteria for working out what spatiotemporal level a certain problem should be placed on. Quoting DeLanda again,
in the example just mentioned, a population level intensive property density can furnish a more stable explanation of the cyclic behavior of the prey-predator system than an organism level 1.
At this point, he returns to the quasi-cause. In his eyes, we can catch a glimpse of mechanism independence in systems which return to their original state even when substantial shocks are administered to it. This is something that occurs in the aforementioned example of predator-prey populations, observed by biologists both in the wild and in the lab. The reason why he invokes the quasi-cause is that these cases show something other than causal relations at work. There's a virtual component hiding beneath it all. Although his focus has been on biological systems so far, he's sure to stress that the same things can be perceived in non-organic systems too, like that of convection in hydrodynamics. Here, the quasi-factors are those of temperature and density gradients, while the quasi-causal ones are bifurcations and the attractors that organize it. With this, DeLanda gets to the end of this half of Chapter 4, seeking to summarize his argument thus far. Basically, the main takeaway is that axiomatic approaches to science, like that of deductive nomology, are essentialist, whilst a Deleuzian epistemology must instead focus on models of problematics. In DeLanda's words,
in Deleuze's approach, the relation between well-posed explanatory problems and their solutions is the epistemological counterpart of the ontological relation between the virtual and the actual.
In a sense, explanatory problems are equivalent to virtual multiplicities, since the virtual is first and foremost the realm of problems. I think this is best summarized by a quote from Difference and Repetition.
An organism is nothing if not the solution to a problem, as are each of its differentiated organs, such as the eye, which solves a light problem.
DeLanda's own examples are the good old salt crystal and soap bubble. Their problem is how to find a minimal point of energy. The actualization is simply a solution, be it a soap film in the case of the latter, or crystalline structure in the former. From this, we can see that there exists an intimate relationship between ontology and epistemology in the work of Gilles Deleuze, something we can go as far as to say is characteristic of his thought. With this, we're done with the first half of Chapter 4 from Manuel DeLanda's book Intensive Science and Virtual Philosophy. I truly hope you enjoyed or learned something. If you feel I got anything wrong or wasn't as clear as I could have been, please do feel free to let me know in the comments so I can do better. In the next video, we'll finish off the chapter and pick up where we left off here, exploring isomorphism through this Deleuzian lens. Until then, bye!